Today I am with the lesson D-block elements and transition elements. In this lesson the points to be discussed are D-block elements, transition elements, and finally we will see some examples. So let's begin. The very first point is D-block elements. What are D-block elements? First of all, let's see the definition of D-block elements. The elements in which last electron enters d orbital are called D-block elements. The number of D-block elements is, from the middle of the periodic table, 38 elements. From the lanthanide series, lanthanum, and from the actinide series, 2 elements, that is actinum and thorium. So total 38, 39, 40, 41. So total 41 elements are D-block elements. Let's see one example, that is scandium 21. Here the last electron is 21st electron. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Then 4s will come because 4s orbital is less energetic than 3d. 3d will come here. So last electron, that is 21st electron, enters d orbital. So scandium is a kind of D-block element. Let's see again the elements in which last electron enters d orbital are called D-block elements. Let's see the next point. Now the point is transition elements. We have learned from the previous point that D-block elements are 41. From these 41 D-block elements, some elements are transition elements. From the D-block elements, which will be the transition elements? Let's see. The transition elements will show variable oxidation state. That means oxidation state will be varied. Number 2, stable ion of D-block elements will have partially filled d orbital. What is the meaning of partially filled d orbital? Let's see. D orbital, this is vacant, no electron is here, and this is fulfilled d orbital. But if the electronic configuration is 1 to 19, then it will be partially filled d orbital. Now let's see some examples. Let's see the element scandium, D-block definitely, but we have to see whether it is transition. Scandium 21, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Last electron enters d orbital, that is why this is D-block element. Here this configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. The orbitals of an energy level are written one by one to avoid possible mistake. Now we have to see whether scandium transition. The ion of scandium is scandium 3+, only the ion scandium 3+, no other ion but scandium 3+. So scandium cannot show variable oxidation state. This is number 1. Let's see here 1s2, 2s2, 2p6, 3s2, 3p6, 3d and 4s. These 3 electrons are removed. 3 plus 3 electrons are removed. So this is 0, this is 0. Now let's see the second point. A stable ion will have partially filled d orbital. This is the stable ion of scandium and it doesn't contain partially filled d orbital. So scandium doesn't follow variable oxidation state and it cannot be a partially filled d orbital. So scandium is dBlock element, but this is not transition element. Compounds of scandium 3 plus are scandium chloride, here oxidation state 3, scandium oxide, here oxidation state 3. So scandium can form compounds with oxidation state +3 only. So it cannot show variable valencies or variable oxidation state. Let's see another example. Now let's see whether titanium transition or not. The electronic configuration of titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 4s. Here 2 and last 2 electrons enter d orbital because this is higher energy orbital than 4s orbital. That is why in the 4s orbital electron will enter first and then electron will enter 3d orbital. But it is written the orbitals of an energy level are written side by side to avoid mistake. So this is a kind of dBlock element because last electron enters d orbital. Now let's see some ions of titanium. Titanium 2 plus, that is compound is titanium oxide, oxidation number 2. Here electronic configuration 1s2. Now let's see here 3s2, 3p6, 3d2, 4s0. That means these 2 electrons will go away. 2 plus. Another ion, let's see, scandium 3 plus. Here 1s2, 3s2, 3p6, 3d1. Like titanium oxide, here the oxidation number of titanium is +3. Another one, let's see, titanium 4 plus, 1s2, 3s2, 3p6, 3d0. This is the stable ion. The compound is like titanium oxide, here 4 plus. Another compound ilmenite. This is another compound of titanium, ilmenite, where oxidation state is +4. This ion is stable ion. Stable ion is indicated by asterisk. Why it is stable ion? Because the last shell is octet fulfilled like neon gas configuration. That is why this ion is a stable ion, but this stable ion doesn't have partially filled d orbital. This is vacant. So considering this, it shouldn't be transition element. But the first point is variable oxidation state. Titanium can show variable oxidation states. Titanium 2 plus, titanium 3 plus, titanium 4 plus. So considering the first point, titanium is a kind of transition element as well. So titanium dBlock element and transition element. Now let's see whether vanadium dBlock element but transition or not. Vanadium 23, 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 4s2 and here 3. 10, 12, 18, 20, 23. Vanadium can form different ions like vanadium 2 plus 1s2, here 3d3, 4s0. That means these two electrons will go away. Vanadium 3 plus, then 1s2, 3d2. Vanadium 3 plus, 1s2, 3d1. The compound is here, it will be 4 plus. The compound will be vanadium tetrachloride, here 4. Another one, let's see, vanadium 5 plus, 1s2, 3s2, 3p6, 3d0. This is the stable ion. The compound is like vanadium pentoxide, here oxidation state +5. First of all, vanadium can show variable oxidation state. So this is transition element. But let's see another point, is stable ion will have partially filled d orbital. This is the stable ion, but here d orbital is not partially filled. This is vacant. Nevertheless, considering the first point, vanadium is a kind of transition element. Vanadium is not only dBlock element but also transition element. Chromium is a kind of dBlock element, but let's see whether it is transition element. Chromium 24, electronic configuration is 1s2, 2s2, here 3s2, 3p6, 3d, 4s2, here 4. This configuration is rearranged to get the stable configuration like this: 1s2, here 3s2, 3p6, 3d5, 4s1 to get half-filled orbitals, which are stable configuration. So to get stability, here rearrangement happens. Now let's see some ions of chromium. Chromium 3 plus, that is 1s2, here 3s2, 3p6, 3d5, here 4, and 4s0, 2 electrons, this one and 1 electron from the 5 electrons, so 3d4. Here the compound is chromic oxide, oxidation number is +3. Another compound, let's see, 3 plus, 1 from here 3 electrons, 1 electron from here 2 electrons, so it will be 3. It will be 3. Chromium 5 plus, 1s2, here 3s2, 3p6, 5 plus, that means how many left? 3d1, 5 electrons from the 6, 5 electrons, so 3d1. Another one, let's see, chromium 6 plus, 1s2, here 3s2, 3p6, 3d0. Here this ion is a stable ion and its compound is like this, and chromium can show variable oxidation states. This is the stable ion which is partially filled. So chromium is following two conditions. So chromium is not only dBlock element but also it is a kind of transition element. One thing can be discussed here, that is 3d orbital is stable. Why it is stable? There is a theory, that is crystal field theory. There are 5 electrons, there are 5 orbitals, 1, 2, 3, 4, 5 orbitals of same energy. These are called degenerate orbitals. When this ion collides with another ion, then these 5d orbitals split. 3 orbitals with lower energy and 2 orbitals with higher energy. This is called splitting of degenerate orbitals. Now the orbitals are non-degenerate orbitals. This is explained by crystal field theory. And now these 3 electrons are arranged according to Hund's rule, that is, each orbital contains 1 electron, which is very much stable, well balanced and symmetrical configuration. Because of this symmetrical configuration, it becomes stable. That is why we can say this is the stable electronic configuration. So chromium is following variable oxidation states, and stable ion of chromium contains partially filled d orbital. So chromium is not only dBlock but also a transition element. Let's see another example. Manganese is a dBlock element. Let's see whether it is transition. Electronic configuration of manganese, first of all, let's see. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 4s, here 2, here 5. Last electron enters d orbital, that is why this is dBlock element. Now let's see some ions of manganese, that is first of all 2 plus, 1 is 2, here we see 3d 5, 4 is 0. These 2 electrons will go away. It's a kind of stable ion because here we see half filled d orbital, that is stable orbital. The compound is manganese oxide, manganese chloride. These are the ions where oxidation state 2 plus, here also 2 plus, and this is the stable ion. Stable ion is indicated by asterisk. Another one, let's see, manganese 4 plus, 1 is 2, here 3d 4 plus, that means 7, here 3 electrons. From the 7, 4 electrons will be removed, then 3 electrons left. This is also stable according to crystal field theory, but this is more stable. Another one, let's see, scandium 7 plus, 1 is 2, here 3 is 2, 3p6, 3d 0, 4 is 0. This is also stable, but to remove these 7 electrons, it needs huge energy. That means ionization energy is too much. That is why formation of 7 plus is very tough, and for this reason this is not a stable ion. Stable ion is this. Now let's see manganese dBlock, because last electron enters d orbital, and it follows 2 conditions: variable oxidation state, that is variable oxidation state, and stable ion will have partially filled d orbital. This is the stable ion which is partially filled d orbital. So manganese is transition element as well. Let's see another example. Now let's see whether iron is transition or not. Iron 26, 1 is 2, 3 is 2, 3p6, 3d6, 4 is 2. There are 2 ions of iron like this. Iron 2 plus, that is 1 is 2, here 3 is 2, 3p6, 3d6, 4 is 0. That means these 2 electrons will go away. Like the compound like ferrous chloride, here oxidation state +2. Another oxidation state +3, then 1s2, here 3s2, 3p6, 3d5. From these two ions, this is more stable ion, where the d orbital is half filled, that is stable configuration, and this stable ion contains partially filled d orbital, d1 to 9, which is partially filled d orbital. So here the compound may be ferric chloride. Now iron last electron enters d orbital, so this is dBlock element. At the same time, it can form variable oxidation states and stable ion with partially filled d orbital. So iron is not only dBlock element but also transition element. Let's see another point. Now let's see whether cobalt is transition element. Cobalt 27, electronic configuration is 3d7, 4s2. Last electron enters 3d orbital, so this is dBlock element. Let's see some ions of cobalt. Cobalt 2 plus, 1s2, 3d7. These two electrons will go away, like cobalt chloride, cobalt oxide, here 2 plus, here 2 plus oxidation state, and cobalt 3 plus, 1s2, here 3d6. From these two ions, this is stable ion because compounds of cobalt 2 plus are available in nature. From this consideration, this is stable ion which contains partially filled d orbital, and cobalt can show variable oxidation states. So cobalt is a kind of transition element as well. Now let's see whether nickel is transition or not. Nickel 28, 1s2, 3d8, 4s2. Last electron enters d orbital, so this is dBlock element. Now let's see some ions. Cobalt 2 plus, 1s2, 3d8, 4s0. These two electrons will go away. Another ion of nickel, that is 3 plus, 1s2, 3d7, 4s0. From these two ions, this is stable ion. The compounds of nickel 2 plus, that is nickel sulfide, nickel oxide, where oxidation number +2. So the compounds of nickel 2 plus are available in the nature. From this point, this is considered stable ion, where d orbital is partially filled. But this is not stable. Here, to remove 3 electrons, it needs huge energy, that is ionization energy. This is stable. One thing can be mentioned here, that is crystal field theory. 1, 2, 3, 4, 5 d orbitals. These d orbitals are split. Here 3 orbitals, 1, 2, 3, and here 2 orbitals, 1 and 2. 8 electrons according to Hund's rule, 1, 2, 3. Now the electrons will be paired, 4, 5, 6. Another 2 electrons left, 1, 2. So it's a very nice, well balanced configuration of electrons in this d orbital. So this ion is stable ion. Now nickel shows variable valency, variable oxidation state, and d orbital is partially filled. So nickel dBlock element as well as transition element. Now about copper. Copper 29, 1s2, 3d9, 4s2. Here rearrangement happens to get stable. 1s2, 3d10, 4s1. Now this is full filled, this is half filled, which is stable electronic configuration. Last electron enters here d orbital, so this is dBlock element. Now let's see whether it is transition. copper plus 1s2 3d10 4s0. It should be the stable ion because this is full filled d orbital, which is the stable configuration. But the compounds of copper plus is very less, but copper 2 plus 1s2 3d9 like this, copper hydroxide. So here 2 plus, here 2 plus, here 2 plus oxidation state. The compounds of copper 2 plus are available in nature. Considering this, it is considered the stable ion exceptionally. Exceptionally, this is a stable ion, contains partially filled d orbital. So copper shows variable oxidation state and stable ion contains partially filled d orbital. So copper is a kind of transition element as well. Lastly, we will see about zinc, whether zinc is transition or not. Zinc 30, 1s2 3d10 4s2. Last electron enters d orbital, so this is dBlock element undoubtedly, and only one ion is seen of zinc, that is zinc 2 plus 1s2 3d10 4s0. This is very stable configuration and no other ion is observed other than zinc 2 plus. And here d orbital is not partially filled, this is full filled. That means this condition is not followed. At the same time, condition 1, variable oxidation state, it is not followed by zinc. Only one ion is observed, that is zinc 2 plus. And in zinc 2 plus, d orbital is not partially filled. So zinc is dBlock element but not transition element. No more today. Thank you very much. Take care.